Hello everyone. So let's get back to the second part of our chapter 19. And in the previous part we talked about what did we talk about? Yes. We talked about buffers. What are buffers? So we talk about they are conjugate acid base systems, right? So they are, if you add a strong acid or if you add a strong base, the pH doesn't change much. And also we learned how to do a calculation when a certain amount of strong acid or a certain amount of strong base is added to a buffer system, how the pH going to change and how to calculate those pH, right? It's kind of a little longer calculation, but if you try to understand it step by step, it makes sense, correct? Okay, so now we are coming to this equation here, that we can find out a pH of a buffer system using this equation, which is like a shortened form, which is called the Henderson Hasselbach equation. Now let's see, in this one you have an acid. Ha represent acid, and H here is the ionizable proton, and A is the conjugate base part. Okay, and then with water going to act as the base going to go ahead and take up the hydrogen, become hydronium ion, and then the conjugate base of the acid. Now for this one, if you try to write Ka, it would be hydronium ion times A minus over Ha. And then we did this calculation where if you isolate hydronium ion concentration, that would represent Ka times Ha over A minus. Okay, and this is the equation in our previous calculation we used to calculate the pH after we calculate the hydronium ion concentration. Ka times concentration of acid over concentration of conjugate base. Now we're going to simplify this by taking log of both sides. Hydronium ion, if you take the log, negative log hydronium ion, which is familiar as the pH, and then this side would be negative log Ka, there would be pKa, and then we do the negative log of, so if you have a multiplication changing it to log, it will become positive, a plus, right? So plus, now before that, yeah, we are still here. Negative log of hydronium ion concentration equals negative log of Ka. Okay, and then you get the negative log of this also. Negative log Ha over A minus. Right, multiplication remains negative log. Okay, and then if you look at this one, negative log of hydronium ion concentration, which is pH, negative log of Ka is pKa. Okay, and then log Ha is the acid, A minus is the conjugate base. Now we are going to reverse this, meaning we are going to make, instead of making it negative, we want to make it a positive for easy purpose, to have a much simpler version of the equation. Instead of keeping it negative, we're going to make it positive. So when you are making negative to positive, you simply reverse this one. So this is acid over base. Now when you make it positive, it becomes acid over base. Sorry, base over acid. I switched it again. Base over acid. So basically, Henderson Hasselbach equation, you can remember pH equals pKa plus log base over acid. Okay, so you can use this equation if you want to calculate pH of a buffer solution. When you know the Ka, you can convert it to pKa, and also knowing concentration of base and the acids. And this is called Henderson Hasselbach equation, very useful equation. Now buffer capacity. Buffer capacity meaning the strength of the buffer. In other words, its ability to maintain the pH following addition of strong acid or base. Now in our previous calculation, we saw by adding a small amount of acid or small amount of base, pH didn't change much. Now for how far that you can keep that without having a dramatical change is the buffer capacity. Okay, the greater the concentrations of the buffer components, the greater its capacity to resist pH changes. So if you make a buffer system with higher concentrations, that can have a higher buffer capacity. Another thing is the closer the component concentrations are to each other, the greater the buffer capacity. Basically, if you can have the same concentrations or you can have a similar concentrations, even if they are not going to be identical. Okay, so that also have a greater buffer capacity. Now let's look at this example, seeing the relation between buffer capacity and pH change. This graph shows the final pH values for 4 different buffer solutions after the addition of strong base. Now let's say you have 4 buffer solutions. 1, 2, 3, 4. And this buffer has a concentration 1 molar. This has 0.3 molar. This is 0.1 molar. This is 0.03 molar. So the buffer concentration increasing. And this is the initial pH of these buffer solutions. So we are adding a strong base. What happened to the pH? When strong base is added, the pH increases least for the most concentrated buffer. So this is the initial pH. Now this is the highest concentration. You add a strong base. So it changed very little for the higher concentrated buffer. 0.3 change next, and 0.1 is a little bit more change, and the lower concentration 0.03, so the change is more. So higher the concentration or the higher the molarity of the buffer components, it has a higher buffer capacity. Okay, the pH doesn't change much. Okay, and the buffer range. Excuse me. The buffer range is the pH range over which the buffer is effective. Buffer range is related to the ratio of buffer component concentrations. The closer the concentration of acid to its conjugate base is to 1, the more effective the buffer. If both of these are 1, 1, that would be wonderful, or 0.1, 0.1, or 0.5, 0.5, like that. If the concentration of one component is more than 10 times the concentration of the other, buffer action is poor. Since log 10 equals 1, buffers have a usable range within plus minus 1 pH unit of the pKa of the acid component. Now remember, we are using acid and the conjugate base for a preparation of a buffer. If you know the pKa, let's say the pKa of a buffer is 4.54. So buffers have a usable range within plus or minus 1. So let's say pKa, for example, 4.54. We have an acid. So the buffer range is going to be plus or minus 1, meaning it works well 3.54 to 5.54 region. So if you want to keep a pH of a solution within this range and you want to conduct a reaction, you would use this buffer system where you have an acid pKa 4.54. Okay. How do we prepare a buffer? First, you need to choose the conjugate acid-base pair. And then the pKa of the weak acid component should be close to the desired pH. Okay. Calculate the ratio of buffer component concentrations. We can use the Henderson Hasselbach equation. pH equals pKa plus log base over acid. So you know the pH, you know the pKa, and then we can calculate the ratio of the buffer component concentrations. And then determine the buffer concentration and calculate the required volume of stock solutions and or masses of components. Once you get the ratio, from that we can calculate if it is a liquid, what is the volume you needed, or if it is a solid, what is the mass of the buffer component that you need. And then mix a solution and we're going to correct the pH to the desired pH of the buffer. Let's look at this with an example. Environmental chemist needs a carbonate buffer of pH 10 to study the effects of acid rain on limestone-rich soils. How many grams of sodium carbonate must she add to 1.5 liter of freshly prepared 0.2 molar sodium hydrogen carbonate to make the buffer? Ka of the hydrogen carbonate is given. Okay, so our pH of the buffer is going to be pH 10. So we cannot use acid like acetic acid or any acid because pH 10 is a base. So you need to use a base and conjugate acid of that. It's asking how many grams of sodium carbonate must be added to 1.5 liter of freshly prepared 0.2 molar sodium hydrogen carbonate to make the buffer. Ka of the buffer hydrogen carbonate is given conjugate acid. So our conjugate pair is going to be hydrogen carbonate is going to be the acid and carbonate going to be the base. Okay, and they're going to come in terms of sodium carbonate. Carbonate comes in terms of sodium carbonate and hydrogen carbonate comes in terms of sodium hydrogen carbonate. Okay, we know both the buffer volume and the concentration. Volume is given 1.5 liters and then molarity also given, concentration of hydrogen carbonate. We can calculate the ratio of components that gives a pH of 10 and then get the mass of the sodium carbonate that must be added to make 1.5 liter of solutions. So you might not have understood anything, but let's look at it step by step. Okay, now we were given Ka of hydrogen carbonate. So what we can do is we can find out the pKa. pKa going to be negative log of Ka, which is negative log 4.7 into 10 to the negative 11, which is 10.33. From the Ka, you find the pKa of our hydrogen carbonate, which is going to be the acid component. Now we are trying to solve the ratio of carbonate to hydrogen carbonate. And this is our Henderson Hasselbach equation. pH equals pKa plus log base over acid. So in this buffer system, hydrogen carbonate is the acid, carbonate is the base. Right? Once hydrogen left, that's going to be your conjugate base. pH was given to us, pH is 10. We found the pKa 10.33 and then the ratio going to be log carbonate concentration over hydrogen carbonate. So pH 10, pKa 10.33. That would be 10 minus 10.33, 0.33. So you can get the inverse log of the ratio. So that would give you ratio carbonate over hydrogen carbonate 0.47. Okay. I hope you understood the math part over here. So 10 minus 10.33, 0.33, and then you take the inverse log of that. That will give you 0.467. Okay. So basically 10 minus 10.33 equals a log of this part. So 10 minus 10.33 is 0.33, negative 0.33, right? And then you take the inverse log of this. That is this part right here. So then carbonate base over acid going to be 10 base 0.33 negative 0.33, and that gives you 0.467, 0.47. So that's how you find the ratio. Okay, this ratio. Now from this ratio we are trying to find out the number of moles of hydrogen carbonate that we needed. Okay, so in our question for hydrogen carbonate, it says 1.5 liter of freshly prepared 0.2 molar sodium hydrogen carbonate to make the buffer. So from this information we can find out the number of moles of sodium hydrogen carbonate. Okay, remember molarity equals moles over volume. So the moles would be molarity times the volume. So volume is 1.5 liter solution, molarity 0.2 per liter. So that gives you number of moles of hydrogen carbonate, right? And so these two are molar ratios, and similarly molarity ratios. Okay, so with this square bracket indicate molarity. Molarity's ratio is similar to molar ratio, number of moles. So 0.3 moles hydrogen carbonate. So in this expression that we just found out, trying to get my pen mode again. Okay, thank you. So carbonate over found hydrogen carbonate is 0.3. 0 equals 0.47. So then the carbonate would be 0.47 times 0.3. 0.47 0.141, right? 0.141. You multiply these two together, 0.14. So we found the number of moles of carbonate. Okay, I hope you understood what we did. We got the ratio of carbonate to hydrogen carbonate, and from that we found out from the given information of our question the number of moles of hydrogen carbonate, right? Molarity given and the volume given, and then that's the number of moles of hydrogen carbonate. We plug that into here, and then we calculate number of moles of carbonate. Okay, now the next question is how many grams of sodium carbonate must she add? Now we know the number of moles of carbonate, so depending on that we can find out the number of moles of sodium carbonate and then the mass. So 0.14 moles carbonate. Remember carbonate. Okay, so basically sodium carbonate will dissociate to give you 2 sodium ions and 1 carbonate. And if you found this is 0.14 carbonate, molar ratio, sodium carbonate also going to be 0.14. Excuse me. So 0.14 mole sodium carbonate, and then the molar mass of sodium carbonate is 105.99. That will give you 15 grams sodium carbonate. We wanted to find out what is the mass of sodium carbonate that we need to add in order to prepare this buffer. So the chemist, just like one of you guys, should dissolve 15 grams of sodium carbonate in about 1.3 liters of 0.2 molar sodium bicarbonate and add more 0.2 molar sodium bicarbonate to make 1.5 liters. First, normally we don't add all the volume. First you add about less than the required volume. You dissolve your solid and then top it up until it become 1.5. And then using a pH meter we can adjust the pH to 10 by dropwise addition of concentrated strong acid or base. Now, after you make your buffer, pH might not be exactly 10. It could be 9.5 or 10.5, for example. And then you adjust it by adding either acid or a base to make it pH 10. So then you have your buffer exactly at pH 10. So that's how we make a buffer solution. Okay. Excuse me. Maybe we can start acid-base titrations in the next session.